There are many commonly occurring series out there that we need in order to take say a bunch of terms that we want to add up that are going to start at some index value and then go up to some unknown index value. So maybe we want to sum from I equals 1 to 1563. And some of those common series are the arithmetic series and the geometric series. Though oftentimes when our certain problems get a little bit more complex, we can see terms that don't expand out in terms of one of those or other very common series. And here's one that I'll just refer to as the ascending geometric series. And what we want to do is we want to solve this. We want to come up with a formula that will produce the sum of those terms without requiring us to actually do any addition. Okay, so if your index goes up to, say, 500, that's going to require 499 total additions, and that's a lot. It would be much easier if there were a formula that could we would input the value of n, in this case 500, and then it would output the sum of those 500 terms without doing the addition. So in this particular geometric series, this is a product of the index value multiplied by a base to the n minus I power. Now I'm going to start with this one with a base of 2, but we're going to generalize this for any base. It could be base 3 or a base of 4 or any non-negative base, as well as no zero base would be perfect for this. Okay, so what these terms look like is when I is 1, you get 1 times 2 to the n minus 1. Second term plus, now the index is 2, I is 2. Here's for I is 1, here's for I is 2. When I is 2, we get 2 times 2 to the n minus 2, and then 3 times 2 to the n minus 3. So what we're seeing here is we're seeing the coefficient increase by 1, while for each subsequent term the power decreases by 1. So for instance, if our sum went from I equals 1 to 3 of I times 2 to the n minus I, then for an index of 1 we'd have 1 times 2. Okay, in this case n is 3, so 3 minus 1 would be 2. This is for I equals 3. I'm sorry, I equals 1. Again, for I equals 1. Now, for I equals 2, our term that we're going to add on to this will be 2 times 2 to the 3 minus 2. So this would be times 2 to the first power. And finally, now we get to I equals 3, and we'll have I times 2 to the n minus I. Well, 3 minus 3 would give us 0. So we see that the powers of 2, that's the geometric piece, are decreasing while the coefficients are what I like to call ascending. And the fact that they're ascending by only 1 makes this convenient. So how do we go about finding a formula for this? Well, one of the things we can do is we can try to build a chart in which we look at several values of n, and then we take a look at the sum for this formula here of I times 2 to the n minus I, I equals 1 to n, and we could actually produce what these sums look like. And that might give us a sense of, hey, based on the value of n, can we apply some sort of expression, some sort of mathematical combination of arithmetic operations to give us that sum value? Well, let's go ahead and do this over in Desmos. It's convenient to do it in here because we could just add in a table. And I'm going to relabel this column to be n. And I'm going to relabel this column to be the sum. So I'm going to type in sum. And I want this to be I equals 1 up to n. And then I want that sum to be of I times 2 to the power of, parenthesis, n minus I. Okay, so we can start taking a look at values of n. N can't be any smaller than 1 because our index starts at 1. Okay, so if you just take the very first term, which would be 1 times 2 to the 0, which would give us 1. First 2 terms, first 3, first 4, and so on. And we see that the differences the difference between each pair of subsequent values, of adjacent values, we'll say, they don't increase by a constant amount. And we can try to come up with formulas for this, but it's relatively difficult to do. So there are at least a couple of different ways that we can approach this. One is to take the series, and I'm just going to apply it to these three terms. I'm going to call this S sub 3. Okay, that's just going to say the sum for the first three terms, which would be 1 times 2 squared plus 2 times 2 to the first plus 3 times 2 to the 0. Now, what I'm going to do is, there's this one trick out there that if you take S3 and you multiply it by something, let's say in this case, what I'm going to do is I'm going to multiply this by 1/2. In other words, that's the same thing as 2 to the negative 1. Okay, this is equal to 1/2. Okay, if I do that, the reason I'm writing it as 2 to the negative 1 is because if I multiply everything on the right-hand side by that, I'll get 1, well here, let me write this out. Here I will actually, with common bases, when I distribute this, I'll add the powers together. So this first term will give me 1 times 2 to the first, plus 2 times 2 to the 0, plus 3 times 2 to the negative 1, because 0 plus negative 1 is negative 1. Now the reason I do that is now if I compare these, S3 is 1 times 2 squared plus 2 times 2 to the first plus 3 times 2 to the 0, and I write below that 2 to the negative 1 times S3. What I'm going to do here is I'm actually going to align the common terms. So here I'll actually put the 1 times 2 to the first over here because those have like powers. Therefore, I could, if I were to combine them, I would just have to manipulate their coefficients via addition or subtraction. And then I'll shift this one over as well, 2 times 2 to the 0. And then this term has no matching buddy in just the S3 equation, so I'll just write that over to the far right. Now what I'm going to do is I'm going to subtract these. And the reason I'm going to subtract them is because we'll be able to reduce the coefficients of the 2 to the first and the 2 to the 0. We'll be able to reduce them by 1. This first term, this is subtracting 0. You can think about this as 0 over here. So subtract these. S3 minus 2 to the negative first times S3. That's just as good as we can write that right now. 1 times 2 squared minus 0 is just 1 times 2 squared. 2 times 2 to the first minus 1 times 2 to the first is equal to 1 times 2 to the first. 3 times 2 to the 0 minus 2 times 2 to the 0 is going to be 1 times 2 to the 0. And then we'll have this last term over here as 3 times 2 to the negative 1. Now the reason I did that is to begin demonstrating the fact that these two outer terms they're going to maintain their original coefficients of 1 and then whatever n is, in this case n is 3, but these two terms right here have a coefficient of 1, and therefore this is just a geometric series, which is the same thing as 2 to the first plus 1. Okay, now let me demonstrate this for a larger set of terms. Let's say we had something like Sn. Okay, Sn would be 1 times 2 to the n minus 1 plus 2 times 2 to the n minus 2 plus 3 times 2 to the n minus 3. And then we're going to have n of these terms. N could be any integer. So ultimately, our coefficient will reach n, and then we'll have times 2 to the n minus n, which is 2 to the 0. Now let's repeat the same kind of idea here. Let's take Sn and multiply both sides by 2 to the negative 1. So what that's effectively going to do, it's going to reduce the power. If you take 2 to the negative 1 times 2 to the n minus 1, I'll just do this off to the side here. If you take 2 to the negative 1 times 2 to the n minus 1, that's going to be 2 to the negative 1 plus n minus 1, which will be 2 to the n minus 2. So negative 1 and a negative 1. Okay, so what that's going to do is it's just going to decrease the power. So this guy will actually shift over and will be 1 times 2 to the n minus 2. Then this term here will be, we'll have to multiply this by 2 to the negative 1. So that will also decrease its power. And again, I'll shift that so that I have 2 times 2 to the n minus 3 over here. Now notice if we take the difference again, all of these terms except the first term and the last term, all of those are going to have coefficients of 1. Maybe I should write in one more term here, just to show how everything shifts over towards the end. We'll have n minus 1 times 2 to the 2 to the first, okay, and then this is the last term over here. So ultimately, this term will be, if we imagine the term before it, it'll be n minus 2 times 2 squared. But if we multiply n minus 2 times 2 squared by 2 to the negative 1, we'll have n minus 2 times 2 to the first. And then this term also will shift over this way, and n minus 1 times 2 to the first times 2 to the negative 1 will become n minus 1 times 2 to the 0. And then this last term, when we multiply that by 2 to the negative 1, that will become the n times 2 to the negative 1. That's like this very last term that we saw right here, this 3 times 2 to the negative 1, where n was 3. Okay, again, the reason we're going to write this is because now we're going to subtract them. And this is just a little algebraic trick. So I think what I'll do here is, notice that we could just factor out a 1/2 and make this 1 Sn minus 1/2 Sn will just be 1/2 Sn. That will equal, okay, so if we subtract 0, we'll have 1 times 2 to the n minus 1. This term right here, all of these terms, when we subtract these, will just give us a coefficient of 1. 1 times 2 to the n minus 2, plus 1 times 2 to the n minus 3, plus so on, plus 1 times 2 to the first, plus 1 times 2 to the 0. And then this last term here, this little stray term, which will be by itself. But the idea is that we've condensed the majority of the terms down, because now notice that this is really just a geometric series. This is our standard good old geometric series. And if I rewrite that, doing the last term first, it's 1 plus 2 to the first plus 2 squared plus dot 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 plus 2 to the n minus 3 plus 2 to the n minus 2. That'll be the largest power. Now, the geometric series formula says that if you add together a series of terms, sorry, this won't be squared, this will be x to the first, plus x squared plus all the way up to x to the n, then this will condense down to x to the n plus 1 minus 1 over x minus 1. So all of these terms that are being added together, that sum can be calculated by just taking the base to the n plus 1 power minus 1 over the base minus 1. That will tell you what the sum comes out to. Now for us, notice that ours goes up only to n minus 2. It doesn't go all the way up to n. But the pattern here is that whatever power this geometric series goes up to, this exponent right here is just going to be 1 unit bigger. That's it, just going to be 1 unit bigger. So in our case, since this is a plus 1, so in our case, since this goes up to n minus 2, this will equal base, which is 2, to the n minus 2 plus 1. Remember, this power plus 1 will give you the power in the right-hand side. So n minus 2 plus 1 is n minus 1. And then subtract 1 from that, that's this minus 1 here, over 2 minus 1. And in this case, these two values here produce 1, and then you get 2 to the n minus 1 over 1. All that to say, okay, now let's come back to what we had. We had 1/2 of Sn. 1/2 of Sn equals this term, 1, I don't even need to write the 1 anymore, I could just say 2 to the n minus 1. Plus, now all of this stuff in the parentheses condensed down into 2 to the n minus 1 minus 1 over 2 minus 1. Now I'm going to leave it like that simply because when we change our base from 2 to say 3, the difference will be that all of these 2's will be 3's. And then finally, our very last term, which is the n times 2 to the negative 1, which, by the way, 2 to the negative 1 is 1/2, so n times 1/2 is just n over 2. And now what I want is the sum of all of those n terms, so I need to multiply both sides by 2. And so if I multiply 2 to the n minus 1 by 2 to the first, that's going to increase the power by 1, which will be 2 to the n. Then I will have plus 2, okay, this will also get multiplied by 2. Right? The denominator is not going to get multiplied by 2, just the numerator. That will, again, increase the power by 1, which is 2 to the n. And then this minus 1 will get multiplied by 2, which will be I'll just say minus 1 times 2. And the reason I'm leaving it like that is because if we were to change this to a base of 3, then these would all of the 2's would simply substitute out 3's. Plus, if you take n over 2 times 2, you just get n. Well, there it is. That's the formula that should generate the sum of all of those terms for us. And what we had to do is we had to use this. There are other ways, of course, but we use this little trick to increase all of our powers by 1 so that all of the previous terms matched up with the next term and the coefficients subtracted to give us a 1, producing a perfect geometric series. So there's a lot of bookkeeping going on here, but I think it's a really cool exercise. And let's go ahead and look back at this in Desmos just to verify. In this column, what I'll go ahead and do is I'll put in the formula 2 to the n plus 2 to the n, well, here I'll just simplify it, minus 2, and that's going to be over 1, plus n. Now they're not matching up, and I think this plus might actually need to be a minus n. There it is. Now notice that this column is actually adding up all of those terms to produce these numbers, but here we're producing the same numbers just by knowing what the value of n is. And the reason that happened is actually here when we did the subtraction, we subtracted 0 minus this, and so this should be not a plus, but a minus. And that means down here, these two should also be minus signs. And one cool little thing here that I could do as well is I could actually combine the two, because I have 2 copies of 2 to the n, and I could write 2 times 2 to the n as 2 to the n plus 1. But again, the goal here is to generalize. And what we want to generalize to is if we have the sum from I equals 1 to n of I times, and instead of 2 to the n minus I, let's just say we have some x to the n minus I. So this base could be anything, and we'll just say where x has to be greater than 0. Now if we look back at what we wrote up here, everything will pretty much be the same, except this step right here. All of our terms on the right up until this point will be fine. But when we actually subtract Sn, instead of having 2 to the negative 1 times Sn, we'll have Sn minus x to the negative 1 times Sn. And that's not just going to be 1 over x. And the reason for that is because when you subtract these, you get Sn minus, well, x to the negative 1 is the same thing as 1 over x times s sub n. And when you factor that s sub n out, you get 1 minus 1 over x. Well, 1 is x over x, so this is Sn times x minus 1 over x. Because if you write 1 as x over x, then you have common denominators, and you can subtract x minus 1 and leave it over x. So here we would actually have x minus 1 over x. So when we multiply by the reciprocal of that, I'm just going to go ahead and write that step down. Okay, so we would have, before I write this final statement, I'll do this off to the side here. This would be x minus 1 over x times Sn equals, and then, okay, now here we would have x to the n minus 1 plus 2 to the x minus 1 minus 1. No, I'm sorry, mixing things up now. This is why we do it numerically first, so that we can understand the pattern. So this will not be 2, but it'll be x to the n minus 1 minus 1 over x minus 1 minus n over x. And the reason this would be over x is because, remember, this last term was n times 2 to the negative 1. So with 2 replaced with x, it'll be n times 2 to the negative 1, which is the same thing as n over x. Now you can kind of do this in 2 separate steps, or you can just multiply by the reciprocal of that, and you would get Sn equals. Here, if you multiplied this guy by x over x minus 1, okay, we're going to multiply both sides by x over x minus 1. So here that'll cancel these two guys out. Here, x times x to the n minus 1 will be x to the n. And then since we're multiplying by over x minus 1, this will be over x minus 1. Then for this next term, we'll also multiply through by x, making that x to the n minus x over, now here we have x minus 1 times x minus 1, which is x minus 1 quantity squared. And then in this last term, the x's will cancel in the numerators, and we'll just be left with minus n over x minus 1. So what we're claiming is that this summation for any base will simply be base to the n over the base minus 1 plus base to the n minus base over base minus 1 quantity squared minus n over base minus 1. And so this is our final formula, which looks quite uncomfortably inconvenient, right? I guess we could combine some like terms if we wanted to, but this gives us a good enough general approximation, or not approximation, a good general formula for it. Let's just go ahead and verify that this works. Go back to Desmos here. So here in Desmos, all I've done is I've replaced the actual base with b. I can't use x because if I use x, it associates it with a graph. So I have this constant that I defined up here, b equals 2, just to check that if we use our formula and plug in b equals 2, we still get the same results. And we do. Now, we can change the value of b. We can change it to b equals 3, and we are matching values on both columns, so we did pretty good. The cool thing about this also is that not only that, but if you start to change these slider values, you can see that we could even do this for fractional x's. It doesn't work just for integers, it also works for fractions because we didn't lay any particular constraints upon x. Of course, it can't equal 0. Oh, I'm sorry, it can equal 0. It does work for b equals 0. I stand corrected. So it works for b equals 0. Well, it's even going to work for negative values. And the reason it works for negative values is really only because we didn't, mathematically, we just operated on x. However, I made one mistake. Instead of x equals x greater than 0, x can't equal 1. X can't equal 1. We get undefined values, and you can probably see why. If our base is 1, then we get b minus 1 in the denominator. So it's not going to work for a b value of 1. In fact, if b is 1, then b to the n minus I will always be 1, and then you'll just get an arithmetic series, 1 plus 2 plus 3 plus 4 plus 5, and so on, and that's a totally different formula altogether. So that resolves our formula here. Let's just change this and say where x is simply not equal to 1. It will work for any value but x is equal to 1. Because once again, if x is 1, then it's just the sum from I equals 1 to n of I, and that's just a basic arithmetic series.